everyone. Today we are discussing this dot and cross diagram, which we also known as the Lewis dot diagram. But first, let's talk about that. What is the effect of these diagrams and what we try to represent? See this video.
This is cesium, the most reactive metal.
Not just that. See this one. Do you ever think that why these elements behave like that? There must be some reasons, right? So we will be starting to talk about that. This is what we have a Lewis dot and cross diagram. Remember, this dot is same thing which you are thinking about. This is your dot, this is your cross, and your diagram will be having these two together. It's not a game. It's not a game, obviously, and we should have a periodic table with us right now. If you can have it, please keep it with you, okay, because we're going to use it. So let's start with the introduction. See, if I want to know this topic, like this dot, this diagram, I should know few things about the elements. Elements, we have so many in periodic table, right? So whenever we talk about element is made up of what? So I have element, any element you can use. I'm not just taking out any specific. It is made up of atoms, right? And atom have two parts. One part is called nucleus, right? And one part we have the shells, that is also known as energy levels. So in this nuclei, we have two subatomic particles known as neutrons, and this is called the protons. Now see, nuclei is present at the center of the atom, and it doesn't participate in the chemical reaction because it's present at the center. It's very difficult to reach there. So only the energy levels, which we also known as shells, have these subatomic particle, which is known as electron, that is going to participate in a chemical reaction. So Lewis dot diagram is a symbolic, you can say it's a representation where we will be discussing electrons, but not all type of electrons. Then which type of electron we're going to discuss? Because some element have 92 electrons, so like we cannot go to each and every electrons, right? So what is the criteria for that? So you know that electrons are arranged in these energy levels, which we call it as electronic configuration, right? Electronic configuration or electronic arrangement. You must heard about this word. If you don't know, let's try to write for the sodium. So sodium is 2, 8 and 1, isn't it? So this is the shells 1, 2 and 3. Like we can say that sodium have 3 shell: first shell, second shell and the third shell. In the third shell it have just 1 electron, right? And we just need that. That's why sodium is having that behavior. Remember this last one? Because it have 1 electron, it's so much reactive. So this is the electron which we needed. It means that we need just outermost shell electrons, outermost shell, also known as the valence shell. Okay, so now we got an idea that what we're trying to do. So let's go with the definition, that what is Lewis dot structure and how we draw them. So let's start from here. Let me write the definition for you. So we can say that Lewis dot structure is the symbolic representation, or you can say visual representations of an element with its outermost shell electrons. Shell electrons, only the outermost shell electrons. Like for sodium, if I want to, it will look like that, just that, right? Now the question is, if sodium is look like that with just 1 electron, the one which will have 2, it means it will have 2 dots, 3 dots, right? So whenever we are trying to write down the Lewis dot structure, see, right now we are talking about just elements, right? In future, in next one, we will discuss the molecule also. So what we need, like whenever we draw Lewis dot structure, what are the 3 things we should have? One is dot, which represents to the electrons. Second is this kind of thing, that is called covalent bond. And the third one, it's like we have written sodium or we are writing carbon. This is called the atomic symbol. So these 3 things we should have whenever we are drawing a Lewis diagram. 3 things: electrons, that is dot. Remember, initially we said cross, right? So to represent the different electrons, like suppose I have hydrogen and I have chlorine. So if I am using a dot for the hydrogen to make it different, I will be using cross for the electrons of the chlorine. That's why it's known as the Lewis dot and cross. Initially, Lewis, the one which Lewis has given, he only mentioned the dot, right? Not cross. It's just for our comfortability or our convenience. We have just to use these dot and cross that so that we can be like very clear that the electron from hydrogens is this one and the hydrogen of chlorine of this one, like that. So the electron of chlorine is this one. So that's what is Lewis dot diagram by definition. We will be applying this on the like some molecules later on, but first let's talk about the periodic table. So see, we have only two blocks, the one group 1 and group 2, and then group 3 to group 8. These blocks we need to write down the Lewis symbols. You can see that according to the number of electron they have, the pink color is the representation of these dots. Now whenever we draw a periodic table, we have two things. One, we have the vertical column, and one we have horizontal, isn't it? So the vertical column represent to the group while the horizontal represent to the period. Now both have their own purpose. Like see, if I want to draw the groups, so group is the representation of what? Like from group, what we know, from group, any group you can choose, you can know the outermost shell electrons, isn't it? That's what we want. Like if I say group 1, it have 1 electron. If I say group 2, it have 2 electron. Group 3, 3 electron. Group 4, 4 electron. So if I will go to the Roman numerals for the group number, it actually represents the outermost shell electrons which we needed to draw the Lewis diagram. Now what is the use of this period? It shows how many shells there are. Like if I say for sodium, sodium is 2, 8 and 1. Its group number is 1 because it is outermost electron is 1, and its period number is 1, 2 and 3, like that. So the period is not what is useful for us for the Lewis dot diagram, only the group number. So if you can if you have a question and you need to draw the Lewis dot diagram, what you will see? You will see the group number, right? From there you will get an idea that how many outermost shell electron it have, and it's very easy then. Okay, let's move on. Now there is one more factor that is called electronegativity. Why we are discussing electronegativity here, I will tell you later. But first understand, electronegativity is a theoretical concept. It is now practically used as some scales. It's a amount of attraction any element can have for the electrons whenever it is present in a shared in a bond form. Like suppose hydrogen and chlorine have a bond, right? Now hydrogen is attracting these two electrons, chlorine is also attracting these electrons. So how much power they are applying to attract that electron, that is electronegativity. And this electronegativity, as you move in a period. So if I say a period, it is horizontal line, means I can say it's left to right, right? So left side we have group number 1, group number 2, and we are going to the right side, it will be like 3, 4, 5, 6, 7, 8, right? So I'm just talking about till 7 because noble gas have very different behavior. So we'll not talk about group 8, group 7. So if I am moving from group 1 to group 7, the electronegativity increase. Remember that, as I mentioned, it will be useful later on. So electronegativity is attraction for the electrons, and if any element have very like 7 electron in their outermost shell, you know what is the rule, right? Octet rule. Every shell want to have 8 electrons. So if anyone have 7, it will have very much attraction to gain that 1 electron and become stable, like the noble gases. So that's why its electronegativity will be higher. But if you in the starting see sodium have 1 electron in their outermost shell, will it have higher electronegativity? No, right? Because its tendency is to lose electron, not to gain electron. Electronegativity is attraction for the electron, like the one who want to gain electron, and sodium don't want. Sodium lose electrons, right? So that is the opposite behavior. That's why starting groups like 1 and 2, they have very low electronegativity, while the groups later on have the high electronegativity. That's what you need to remember, okay? I'm not writing the definition. If you need it, I have said it, so you can just Start from there. Now let's talk about the whenever we draw Lewis dot diagram, we need to follow certain steps, right? So we'll talk about that. First step we need to go through very first one, okay? That is the finding the outermost shell electrons. Most important thing. Okay, if you have find it out, second you need to go to the like how many more electron we needed, and it will be valid for the every atom in the molecule. Okay. Third one, after finding it out, we need to find out how many bond they will form, number of covalent bond they're going to form for their stability. Then we need to draw the structure. To draw the structure, see, some atom will be present at the corners or terminal, and some atom will be present in the center. So we should know which one is central atom, and then which one is the terminal one. And last not the least, you need to write down like draw the dots. Okay, so one by one I am moving like very quickly. Like I will tell you about the valence electrons. As I mentioned, valence electron, the outermost shell electrons, like for if you go to the group number 1, it have just one electron in their valence shell. In the same way, group 2, it have two electrons. Group 3, remember that these groups I am writing, like which I am right now saying, it is in Roman numerals. If you will use English number, then it's kind of difficult, so it's better if you use this number. Okay, like for the group number 3, which is in English it's 3, in Roman numerals third A, sorry. So it's 3 electrons. And the same way, fourth A will have the 4 electrons, 5A will have 5, 6, and say, like I will give you one example of each. Sodium is here, so it's have 1 dot. We have the magnesium here, that is 1 and 2 dot. We have aluminium here, 1, 2, and 3 dot. We have silicon here, that is 1, 2, 3, and 4 dot, like that. Got it? So this is how we find the valence electron. Now, how many more electron they needed? See, okay, now since you know that how many electron they needed, according to that we will form the covalent bond. Like that, for example, we already have seen this one, chlorine, right? So chlorine, we know it has 7 electrons. It means it need one more electron. It will form one covalent bond. Now remember that one more electron. Now remember that chlorine will be sharing its one electron with another element, right? So remaining six electron will be there. They will not participate in the bond formation. This one electron will be shared from, like suppose this is hydrogen, right? And these two electrons will form a single bond. Remember that one covalent bond is made up of the two electrons, one from this element, one from this element. It's two different elements, right? And they're going to form the covalent bond. This covalent bond, it's not necessary it will be always just one bond. Like in case of carbon, you will see between carbon and oxygen, we have two bonds. And when the first bond form, it's known as sigma bond. Remember that this name. While if we have two bonds like double bond, there will be one sigma and one pi. In the same way, if there is nitrogen and nitrogen molecule, you have seen there is a triple bond according to the requirement, because nitrogen needs 3 electrons. Both nitrogen need 3 electrons, so they're going to share the 3 electron and 3 electron from each. So three bond. In that case, the first bond in which is in between, it's sigma, and the remaining two will be the pi. So just remember, if it is single bond, one bond, it's sigma. If it is double bond, it's one sigma, one pi. And if it is triple, it's one sigma and two pi. Clear? So that is what we will going to have in the number of bonds. Next, we have choose a central atom. We have certain molecules like CO2 where we need to find out which molecule is present at the center. Like why I'm saying CO2, let me just tell you. In case of CO2, I have two elements, right? These two, carbon and oxygen. Now which will be present at the center, that is the main question. See, there is a concept I told you, electronegativity, and it was initially mentioned that by some scientist, chemist actually, who said that less electronegative should present at the center, while the more electronegative should present at the terminal. So according to that, the structure for this one, carbon is less electronegative. How do I know carbon is less electronegative? See, if you check their electronic configuration, you will get basically an idea. 2,4 is the electronic configuration of the carbon, and 2,6 is the electronic configuration of oxygen. Oxygen needed only 2 electrons to be stable, while carbon need 4. Which one is more easy? For oxygen, right? So that's why it will have more power. More power, more electronegative. right? So I know that oxygen is more electronegative, it should be at the terminal, and the carbon should be at the center. But this theory is actually, it's not valid for the most of the elements. Like for example, I have the water. So in water, oxygen and this one, which one is more electronegative? Oxygen, right? But oxygen present at the center, isn't it? So that is a problem. So this choose a central atom. I will give you better idea than this one, that how do we find it. See, we will be like, first of all, see the element you have. The element, according to the element you have, you can just draw it. For example, the same example we have taken, that is CO2. I have the molecule of CO2. Can you see? Now CO2, carbon need 4 more electrons, oxygen need 2. Now see, they need to be satisfy each other. How I can satisfy this carbon and the other oxygen also need 2, right? So if I by anyhow if I can put this oxygen from here, like I am putting it here from here. Now, isn't it the better idea? So that these two electrons will be given to this one, shared to this one will be shared to this one. Now both are satisfactory. So you can just see how many electrons they require, and according to that you can arrange them, organize them so that they will be satisfy each other. Like for case of water, I know oxygen need 2, hydrogen just need 1. So it means that oxygen will be forming 2 bonds, one with this, like that. Okay. So that's how we do that. Now, last one is the remaining electron around the outside atom. See, now we know that not every electron of the outermost shell participate in the bond formation. Some will be still there, right? So what will happen to them? They will be just put it there, right? For example, I have a molecule of chlorine. Chlorine form only one bond. So the 6 electrons is still there, right? We need to just organize them. They are normally present in the paired form. Two like that. Okay, that's how we do that. Like let me draw for the this one. So this one is form bond and remaining 1, 2, 3, 4, 5, 6 like that. Got it? So this is we have done until now for the elements. Let's try to use this on the some molecules. I will draw some structure. You're going to be first solve it and then I will help you. First is NH3. Second I have water and then I have CH4. Try. Okay, so let's see for the first nitrogen. 5 electrons, only 3 bond going to form, 1, 2 and 3. So the 3 electrons, 2 electrons still there, which will be in paired form. It is forming bond with the hydrogen, so I am just using this cross to show the hydrogen elements to you. This is the way to represent the dot diagram, but now we use much better, that is skeletal form. In skeletal form, the bond we show them as a bond, not with this dot dot diagram. So the NH3 will look like that in skeletal form, like, isn't it much better than water? CH4. So this is how we do that. So I hope this is clear to you. Try with some example and please share your feedback, right? If you find this video helpful, please share, like and subscribe.